Hi there. Welcome back to our course on advanced quantum mechanics. This is lecture number 15. Remember, we calculated the eigenbasis of the position operator. So we solved this equation. And we did so by choosing the basis of the Bn, which can be the eigenbasis of a harmonic oscillator, for example. And so we solved using the Bn basis. But remember that this is just the basis in the Hilbert space. It can be used for the harmonic oscillator, but it could be used for any other system, of course, too. It just so happens that it is the eigenbasis for the Hamiltonian of a harmonic oscillator with suitably chosen parameters. So what we found is the eigenbasis. That is to say, we found for each position eigenvector its wave function. So this position eigenvector in the Bn basis, and they are, let me just write Hermite functions. Hermite functions. It doesn't matter exactly how they look like at the moment. And we also found that the spectrum of the position operator is only continuous. So it's the continuous part of the spectrum. There is no point spectrum, and it is the real line. So therefore, what we have is that we have position eigenvectors, let's call them x, and another position eigenvector might be called x tilde, and they are out of a continuous spectrum. Therefore, they cannot be properly normalized. They can only be continuum normalized. So we have here the Dirac delta instead of the Kronecker delta. And we can choose the x and the x tilde to be any real number here. And we also have now a resolution of the identity in terms of the position basis, minus infinity to infinity, or sometimes we will just write r for the real numbers here, like this, dx. Now, knowing all of this, we can now rewrite quantum mechanics entirely in terms of the position representation. So let's do this. So using this resolution of the identity, we can now write, for example, arbitrary vectors psi in the Hilbert space as identity acting on psi, which is the integral over r of x psi dx. This is, of course, the wave function of psi in the position basis, right? Whenever we have a state on the right and then some basis on the left, we call these overlap functions the wave functions. So this is the position wave function of our abstract state psi in the Hilbert space. And so we can now write that psi is a linear combination of the basis vectors dx, right? I just rewrote that same equation here, where psi of x is equal to the overlap x and psi. Now, we can also use the resolution of the identity to express inner products and operators in the position basis. Let's do this. It's the same Let's do it now explicitly for the position basis. Later we'll do it a little faster for the momentum basis, and then for all other bases. I assume you know how this works. You just express your identity in terms of the basis vectors and then insert that wherever you want to change to that corresponding basis. So for example, let's look at the scalar product. Let's write it out abstractly first, and then let's rewrite it in the position representation. By the way, when we say position representation or position basis or position eigenbasis, it's all the same. So position basis, position eigenbasis, or position representation is all the same. All right, so we take, let's say, the inner product between two Hilbert space vectors, psi and phi. Then how do we write that in the position representation? Well, insert a resolution of the identity in terms of the position eigenbasis. So it's psi, and then you put the identity here, and then phi. And this is integral psi, and then x, here comes the resolution of the identity, and then phi, and then dx, and this is to be integrated over r. Now, what are these two terms? Well, this we recognize as the position wave function of the abstract state phi. So this is phi of x. And what is this? Well, it's not the position wave function of psi, because for that the x would have to be on the left and the psi on the right. But it's a complex conjugate, of course, of it. So this then is psi of x star, right? Recall that when you have the inner product between two states alpha and beta, then this is equal to, I need more space, like this. This is equal to what you get when you write them in the other way around, but complex conjugated. Okay, so that's what we used here to recognize that these are these two wave functions. So what we have is that the abstract inner product between the abstract states psi and phi is the integral over the real line of psi star of x phi of x dx in the position representation. Remember that if we had chosen the Bn basis or any other discrete basis, we wouldn't have an integral here, we would have a series, a sum, an infinite sum. So what we can also tell from this is that the criterion for a vector to be in the Hilbert space translates in the position basis into a concrete criterion, which is square integrability. So what we have is this. If psi is not infinite, if the length of a vector is finite, then we have that psi is in the Hilbert space, right? So we knew that. What does this mean for the position wave function of psi? So in x hat basis, this statement is, well, we used the usual trick, introduce a resolution of the identity. Namely, we have that psi equal to psi identity psi equal to integral from above. We know that this is the integral of psi star of x, psi of x dx, which is the integral of r of psi of x modulo squared dx. So if we want this to be, finite. Oof, what happened here with the software? Okay, so we want this to be finite. If that's true, so in other words, this means i.e. psi of x is what is called square integrable. then psi, it's a difficult angle to write when I'm at the bottom of the page. Then psi is in the Hilbert space. So you see the criterion in the position representation is that the wave function has to be square integrable. If it is, our state, our abstract state is a vector in the Hilbert space. Now, what about operators? Let us look at an abstract operator in the position basis. So operators in the x hat eigenbasis. Well, let's choose one. Let's say e.g. some operator q hat. This could be the position operator, could be the momentum operator, could be the Hamiltonian of some system, could be an angular momentum, whatever observable we may want to choose. So q hat is some abstract operator on the Hilbert space. We want to know how it looks like in the position representation. Usual trick, put resolutions of the identity. For operators, we need two of them because the operator has, so to speak, two sides. So we write this as 1 q hat 1. And we use the resolution of the identity in the position representation. I'm sure you see where this is going. So we have here x, q hat, and then another resolution of the identity. Let's call these the x tilde vectors, and then we have dx, dx tilde. All right, this is what? If we had chosen a discrete basis, then this would be Bn, this would be Bm, and therefore this would be a matrix element. We still speak of matrix elements informally, even when we're dealing with a continuous basis here. So we will define this to be by definition q hat of x and x tilde. Okay, so this is just what we will call it. So we will say this is equal to x q hat x tilde. And then the definition is, we say these are the matrix elements matrix elements of q hat in the x hat basis, in the position basis. Even though, of course, you know, since the x and the x tilde are continuously labeled, we shouldn't really think of this as a matrix in the usual sense. There's another definition, which is a definition that mathematicians use. See, physicists would say matrix elements, implicitly meaning if it only were discrete, then we could call it properly matrix elements, but for the continuum, we don't bother coming up with a new definition. Mathematicians would say that q hat of x and x tilde is called the integral kernel of q hat in the x hat basis. So that's the same thing, matrix elements or integral kernel. And you can see why it would be called integral kernel, right? Because it's a quantity made for integration. Just like a matrix is meant to be applied to a column vector and then summed over. Here we have this continuous version of a matrix. It's meant to be multiplied with a function and integrated over. you know, we have these x and x tildes here. So let's see, what is the integral kernel, for example, of the position operator? So integral kernel of x hat. Well, let's see. What do we have to calculate for this? For this, we need to calculate the matrix elements of the position operator in the position basis. And what might that be? Well, when x hat acts on x tilde, remember we have x hat acting on x tilde produces the eigenvalue x tilde, right? So this is then, and that's just a number, this thing is in R, so we can pull this out. So what we have is that this is x tilde, x tilde. But remember that these guys are continuum orthonormalized. So this is x tilde, delta of x minus x tilde. And we can then also say that this is x times delta of x minus x tilde. Because the delta is only non-zero when x is equal to x tilde. So we may as well write an x over here. Now what we notice here is that these matrix elements vanish when x is not equal x tilde, right? Because we have the delta of x minus x tilde. So that means that as far as we can speak of a matrix here, it is diagonal. So we notice, or we say, x hat is diagonal in the x hat basis. If this were a self-adjoint operator with a discrete spectrum, this would be a triviality. But it's a continuous spectrum, and I'm just saying here that we are still using that terminology in practice. Now, that's all good and fine, but what about the momentum operator? So now, what is p hat in the x hat basis? What is its integral kernel? What are its matrix elements? So what we want to calculate is, in the position basis, what is the momentum operator? There are infinitely many ways to calculate that. One way to calculate it would be, and why are there infinitely many ways? Well, because you can choose infinitely many bases to calculate that in. So one way to calculate is to use that we already know the p hat operator, its matrix elements. We already know these matrix elements in the Bn basis. So we can just change bases. What would that look like? By the way, one of you asked on Piazza, why do we change bases so much? Actually, it's super important. It might look tedious, but there are two reasons why we change bases so much and why I put so much emphasis on how that works. One reason is obviously the changes of bases can be confusing if you're not completely familiar with what's going on there. So I try to be careful with that. But secondly, changes of bases are usually the heart of any quantum mechanical problem. Let's say somebody gives you the Hamiltonian of a molecule and asks, what's the spectrum of it? What kind of light will it absorb? What kind of light will it emit? Well, usually you're given the Hamiltonian of the molecule in the position basis. You say, here's a nucleus, there's a nucleus, and the electrons whiz around. And all of that is described in the position basis, where you have the various potential terms of various things that occur in there. And then you want to know what's the spectrum. And what they mean by spectrum is the spectrum of the Hamiltonian. It's the energy levels of the Hamiltonian that are measurable when you illuminate a molecule. So what you have to do basically is just to change from the position representation to the energy representation. You go from the eigenbasis of the position operator in which you're given the Hamiltonian, and then you need to find what is the eigenbasis of the Hamiltonian. What are the eigenvalues of the Hamiltonian? Almost always, solving a quantum mechanical problem constitutes essentially of going from one basis to another basis. All right, so let's be careful about changing bases. At the moment, we want to know how does the momentum operator look like in the position basis. Well, one way to calculate it is to say, okay, let's insert the resolution of the identity in the Bn basis because we know what the momentum operator looks like there. So let's do this. We start with x, and then identity p hat, identity x tilde. Okay, that's the same as, I mean, that's the matrix elements that we want to calculate. And then we expand that in the Bm basis. So then we have that this is x, and now I insert the resolution of the identity here, the Bn's. And then we have here the p hat, and now another resolution of the identity in terms of Bm, and then we have here the x tilde. See, these guys we calculated in the previous lectures. In the previous lecture, these are Hermite functions. Hermite function. And the same is true for this one. It's just a complex conjugate of it, but the Hermite functions happen to be real, so they're actually the same here. Hermite function. And what is this? Well, these are the matrix elements of the momentum operator in the Bn basis. And remember, we worked out what that is. And what we had is that this is the following matrix. It's I, H bar over L, L setting the units. And then we had here 0, 0, 0, 0, 0, and so on. And then here we had minus square root 1, minus square root 2, minus square root 3, etc. And here we have square root 1, square root 2, square root 3, etc. Zeros here, zeros there. That was the matrix. So we are done, except that it's super tedious. But apart from that, we have it explicitly. We just calculated what the matrix elements of the momentum operator are in the position basis. All we need to do is take these Hermite functions, which depend on m, Hermite functions depend on n, and then sum them up left and right with this matrix. So it's basically a row vector to the left, column vector to the right, and the column vector depends on x tilde, and the row vector depends on x. And at the end, you get a function of x and x tilde when you work all of that infinite series out. Now, that can be done, but it's some mathematical acrobatics that doesn't tell us anything about quantum mechanics. I will leave that tedious work to textbooks, and I will just tell you what the outcome of that is. This turns out to be IH bar d by dx and then delta of x minus x tilde, right? It's got to be something that depends on x because of this, and something and also depend on x tilde because of the occurrence of x tilde over here. Well, so what we have is that the matrix elements of the position operator in the momentum operator and the position representation are given by this expression, IH bar d by dx of the Dirac delta. what is the derivative of the Dirac delta? It turns out it's not hard to handle. The reason is that we know how the Dirac delta works. It unfolds its power when you multiply it with a function and integrate it over. And if we have the derivative of the Dirac delta multiplied with a function integrate over, when that occurs, then we just have to use integration by parts so that the derivative acts on the function rather than on the Dirac delta. That's what that expression means. So, what do we have? So, what do we have? We then have that p hat is equal to identity p hat identity, which is, we insert the identity in the position representation, x, and then we have p hat x tilde dx tilde, and that is then equal to integral, this is over r, and this is over r. And now we know what this is, so we can fill that in, and we obtain that this is I h bar d by dx, the derivative of the Dirac delta, x minus x tilde, and then multiplied with x tilde, dx tilde. Now this looks almost as if it was also diagonal, right? But it turns out that the derivative of the Dirac delta doesn't qualify to be called diagonal. It's not quite right to say that the derivative of the Dirac delta is vanishing when x is not equal to x tilde. And that's because of the derivative. The derivative actually knows about neighboring values. So actually the momentum operator is not diagonal in the position representation. Now all of this looks pretty abstract, but we can apply this and see how it all plays out in practice. So let's see it in action. Let's see it in action. So let's write down some abstract equation involving the momentum operator and then solve it or re-express it in terms of the position basis. And I hope that this will be illuminating, because this is something that has driven me crazy when I first learned quantum mechanics, when people told me that the momentum operator is equal to some derivative operator, minus IH bar d by dx. And I thought, what the heck, why would that be so? Now we will see how that arises and what really is going on behind the scenes here, how all of this is just a matter of representation theory, or just a matter of choices of bases. So let's see it in action. Consider the abstract equation. Consider the equation phi equal to p hat psi. So we just apply the momentum operator to some state psi and get some state phi. Okay. Consider this is an abstract equation, right? No basis has been chosen here. Consider this abstract equation and put it in the x basis. In the x hat basis. Okay, so that's the challenge. We go from the abstract to the concrete. I want you to be able to freely move between abstract equations like this and the concrete equations that you get when you choose a basis. Remember, the abstract is great for general arguing of what's going on. The concrete is great because it's explicit differential equations and so on that you can solve with the methods of differential equations. So for practical purposes, choose a basis. In order to understand more deeply what's going on, write it in a basis independent way. Okay, so this equation in the position basis, what does it become? Well, we write the position basis from the left. So we write x phi equal to x p hat psi, right? Are we done with writing this equation in the position representation? Not quite, right? We recognize what this thing is. This is, of course, phi of x. It's the position wave function of the state phi. But here we don't have position wave functions yet. So we continue. We write this as x p hat identity psi. So we can write now that phi of x is equal to, and now I'm writing out this resolution of the identity in the position basis. So this is then the integral over r of x p hat, and now comes the resolution of the identity here. X tilde psi dx tilde. So here we have psi of x tilde. This is the position wave function of the abstract state psi. It's like a column vector except with a continuous label. And this here, remember what it was. It is IH bar d by dx delta of x minus x tilde. Sorry, this is x tilde. Oh, I hope I got that right up here. Yeah, I didn't. This needs to be x tilde. Okay, this is just how it comes out. Oh, do I have it correctly here? No, here neither. Okay, so this would be d by dx tilde here. Okay. All right, so what do we have? We have phi of x equal to integral r, and then IH bar d by dx delta d by dx tilde delta of x minus x tilde, whatever that function is, times psi of x tilde dx tilde. And now comes into play what I mentioned earlier about what the derivative of the Dirac delta is. You see, here we have the derivative of a function, or a distribution technically, and here we have a function. Let's integrate by parts. What we obtain is that this is minus the integral IH bar, and then it's just the delta of x minus x tilde, and now we've thrown the derivative over to the other side, d by dx tilde, integration by parts, right? Psi of x tilde, dx tilde, and then technically we also have the term which is IH bar, delta of x minus x tilde, psi of x tilde, from minus infinity to plus infinity. But of course, at minus and plus infinity, the Dirac delta cannot peak. It peaks at a finite value. So therefore, this thing is equal to 0. And we are just left with this. But what is this? This is minus IH bar. Well, and then what? You see, it's a function, namely this function, the derivative here, this function multiplied with the Dirac delta, which peaks at x. So therefore, we get rid of this integral. This is just an ordinary Dirac delta, not an integral, not a differentiated one. So this is simply d psi by dx, and that's it, right? We simply have that this is minus IH bar, or let me write it out a little bit more suggestively, as d by dx of psi of x, right? It's not x tilde, it's x, because the Dirac delta has chosen among the integration values of x tilde the one where it matches the x. So overall, we have that phi equal, oh, let me write it more nicely. Therefore, we have that the abstract equation phi equal to p hat psi is also, namely in the position representation, it is phi of, yeah, this is happening when I don't see what I'm writing. So it's also phi of x equal to minus IH bar d by dx psi of x. And all of this is true for all phi and psi. So what we see is this is abstract, and this is concrete. Remember, concrete meaning inner basis. Now, you see, this motivates a definition. We see here that the abstract action of p hat, of mapping a vector psi into a vector phi, is accomplished in a basis by taking the wave function, and in the position basis, it's accomplished by taking the position wave function of psi and then acting with the differential operator minus IH bar d by dx on it. So shorthand notation is this. Shorthand notation. We say, we write that p hat, just a sec. Let me write it like this. We write that phi of x is equal to p hat dot psi of x, where p hat dot is equal to minus I h bar d by dx. See, so what we are saying is that the action of the p hat operator in the position basis, and all of those words are encoded in this little dot over here. We are saying the action of the p hat operator in the position representation, signified by p hat dot, is to differentiate the wave function psi of x and multiply it with minus IH bar. Okay, so this is obviously the right thing to do, because as we see here, the abstract action of p hat on psi is accomplished by doing this differential operator. So what we see here is that when people say the momentum operator in quantum mechanics is minus IH bar d by dx, what they really mean is that the action of the abstract momentum operator on some state psi can be accomplished in the position basis by doing this. In a different basis, the action of the momentum operator would be different. For example, in the momentum basis, as you will see, it will be different. So for example, what is now the shorthand notation for the position operator? Shorthand or action, shorthand action of x hat in x hat basis, in the same basis therefore? Well, let's look at it. Let's say we have the abstract equation. The abstract equation could be like this. Phi is equal to x hat acting on psi. That's the abstract one. And now let's write this down concretely in the position basis. So we have x phi equal to x hat psi. And therefore we have phi of x, right? This is just phi of x is equal to, and now this x hat acting on the x to the left, remember it's self-adjoint, so it can act equally to the, it acts equally to the right and to the left. So this just pulls out the eigenvalue. So we get x psi. So we have phi of x equal to x psi of x. And therefore, we see, phi of x is equal to the action of the abstract position operator on the wave function psi of x, where x hat dot is equal to x. Just multiply the operator of multiplication with x. Okay. Remember that this dot notation always implies that you've chosen a basis. The x hat dot in the position basis is like that, but the x hat dot in some other basis will be different. And I trust that you can do all those things very easily now. So we have the position representation all wrapped up. What about the momentum representation now? So what are the spectrum of the momentum operator and eigenstates P? We could do the same thing as we did for the position operator. We could calculate this in terms of the Bn basis. And we would have to deal with these Hermite functions again, and we would get this terrible matrix, etc. So we are not going to do this, because now we have the position basis available. So let's calculate it in the position basis. Calculate them in the x hat basis. At this point, you're probably already very familiar with changing bases. All right, so how do we do that? Abstractly, we have that p hat p equal to eigenvalue p has to be solved. This is the equation that we abstractly need to solve. We need to find out, for example, what real numbers p can occur here. So we do this in the position basis. So we obtain x p hat p equal to p and then xp. So I've just multiplied from the left with a bra vector of x. We get this. Now, let's insert a resolution of the identity here. So we can put here, let's just write it out. So this means x p hat identity p equal to p x p. By the way, this thing here is what we really want to know. This is a momentum eigenstate in the position basis. Okay, this is what we need. What we want to find out, what is the momentum eigenstate's wave function in the position basis? Now while we are at it, let's give these things a name. So this is psi p of x. So this is momentum eigenstate p, wave function of momentum eigenstate p in the x hat basis. And that's what we want to calculate. Now, let's insert a resolution of the identity in the position representation over here. So we obtain that this is the integral x p hat x tilde p equal to p, and then we have here psi p of x. And here we recognize, aha, this is equal to psi p of x tilde. And what is this? Oh, there's a dx. So let me clean this up. We have a dx tilde, like this. Okay, and this matrix element or integral kernel, we know what it is. It's I h bar d by dx tilde of delta of x minus x tilde, right? So what do we obtain here? We obtain, therefore, that the integral over R of IH bar and then d by dx tilde of delta of x minus x tilde, whatever that function is, it gets multiplied with psi p of x tilde, our wave function that we want to calculate, p psi p of x. We can evaluate this further with the usual trick. We use integration by parts and throw it on the other side. So what we obtain is that this is, and I'm not going to do all the details again of that step, we obtain that this is minus IH bar, let me just write integration by parts, minus IH bar d by dx of psi p of x is equal to p psi p of x. This is a differential equation. And we should be able to solve that differential equation. Indeed, it's easy. It just says that if you differentiate the wave function psi p of x, then you get up to a factor of minus IH bar p. You get the wave function again. So therefore, it clearly has to be an exponential function here. So from that, we can conclude that psi p of x has to be up to a normalization constant e to the power of I xp over h bar. Right? Because if you differentiate that with respect to x, then you get down an ip over h bar, or you get a p divided by minus ih bar. So you just get this. All right, so that's what we have here. And this is, by the way, remember, it is xp. It is a momentum eigenstate in the position eigenbasis. Right, let me just show you again. Over here, that's where we introduced it, or here, right? The momentum eigenstate in the position eigenbasis. All right, it's a plane wave. You see, e to the power ixp over h bar, that's a plane wave. Now, we also need to calculate this. What is it? Well, I need more space. Well, we have to normalize our state, right? So what we need is that psi p, psi, well, no, that's not how we write these things. We write it like this. We have p tilde. The abstract states are continuum orthonormalized, p minus p tilde. And this is, of course, p and then the identity and p tilde. And this is, of course, the integral over r. And then we have here p x p tilde dx. And this is the integral over r of psi p of x star times psi p tilde of x dx. And this, therefore, is equal to n star, the complex conjugate of e to the power of, and then minus ixp over h bar, because we know already what psi p of x is. it's this plane wave, and we now have to complex conjugate it, and we multiply that with n e to the power of I x p tilde over h bar. Sorry, that needs to be integrated over r dx. So this is n star, and then the integral over r of e to the power of minus I x p over h bar. Sorry, this is a p minus p tilde here, p minus p tilde dx. Now, this has to be, if you remember, this has to be equal to the Dirac delta of p minus p tilde. Let me just write it here. Has to be Dirac delta of p minus p tilde. Now, let's remember that when you do the integral over the real line of a plane wave, e to the power of ab dA, then this is 2 pi Dirac delta of b. If we use that, we can then conclude that n, the normalization constant, has to be 1 over square root of 2 pi h bar, up to a phase, but that phase is chosen equal to 1. So therefore, we now have the final solution here, that the momentum eigenvectors in the position basis take this form. This is what we also call psi p of x, and it is 1 over square root of 2 pi h bar, and then e to the power I x p over h bar. You know, of course, that we could take the complex conjugate of that, and then we obtain the position eigenvectors in the momentum eigenbases, right? We can go one way or the other just by complex conjugation here. So let's do a quick example of this, and then we'll be done for today. So example. Let's say we start with this. Given psi of x, which is also, of course, this, then what is psi tilde of p, defined to be the momentum eigenfunction of the momentum wave function of the same state psi? Well, let's just calculate it straightforwardly. What we have is psi tilde of p is equal to, by definition, p psi, which is, if we put in a resolution of the identity, it is this, and therefore it is p, and then the resolution of the identity, x, and then psi and dx, integral over the real line. And what is this then? Well, it's the integral over the real line of the complex conjugate of what we just calculated here, right? So this is 1 over square root of 2 pi h bar e to the power of minus ixp divided by h bar. That's this matrix element here, or this overlap function here, times, what is this? Well, the position wave function. So we have psi of x dx. So psi tilde of p is this. This is the origin of the Fourier transform in quantum mechanics. This is why the Fourier transform occurs in quantum mechanics. It's because the Fourier factor here, you see, obviously psi tilde is the Fourier transform of psi. This factor here just happens to be the overlap between the eigenvectors of the position basis and the momentum basis. It's this thing up to that normalization prefactor here, right? So that this Fourier factor just happens to be that overlap between the position and the momentum basis. And now you see a general structure here in quantum mechanics. Whenever you change bases, you get the analog of a Fourier transform. You see, if you change from the position to the momentum basis, as we did now, you get these overlaps between the x basis and the p basis, and they happen to be plane waves. And that is defining then a Fourier transform. But what would happen if we went from the position basis to the Bn basis, for example? Well, the Bn basis are a basis of Hermite functions. I mean, the position eigenvectors in the momentum in the B basis are Hermite functions. Therefore, the analog of that change of basis formula here wouldn't be a Fourier transform. It would be what is called a Hermite transform, because instead of the plane waves, we would have Hermite functions here. And you see the general structure now, that in quantum mechanics, you can have bases, any number of bases you want. Sometimes the eigenbasis of an angular momentum operator, or a Hamiltonian, or position, momentum, or harmonic oscillator basis, or whatever. Whenever you go from one basis to another, you get some sort of transform. And sometimes it happens to be a Fourier transform, sometimes it happens to be a Hermite transform, but any kind of transform can occur. Laplace transforms and Laguerre transforms, whatever, they can all occur. It's just changes of basis in quantum mechanics. Now, just to conclude, we found a solution xp. We found a position eigenfunction of a momentum eigenvector. We found a position wave function of a momentum eigenvector for all p in R. So therefore, there was no restriction on what the value of p was, right? So therefore, eigenbases, well, let me just write the spectrum then. So therefore, what we have is that the spectrum of the momentum operator is a purely continuous spectrum. It's the continuous spectrum only. There's no contribution from the points, there's no point spectrum. And this is R. So the spectrum of the momentum operator is the real line. And what we have is that we can now also write down resolutions of the identity in terms of momentum eigenvectors. And you see, this is our third basis. After the Bn basis, the x basis, and the p basis, any other basis, it works the same way. We can jump between the discrete and the continuous, and the continuous, and the mixed ones as well. It all works the same. Okay, this is as far as we get today. See you in 2 days.